Well, as long as the Blackboard collaborates from blacking out and you haven't, right? That would be a very bad thing. All right, well, we are going to be looking at some more advanced exponential and log equations. We have already solved both types, but they've kind of been special cases. One type involved the one-to-one property. The other involved rewriting. And there's going to be kind of some nuances of those within the techniques that we'll be investigating today. And there's kind of a variety of options in which you can take when solving at least the exponential equations. And I'm going to show you two methods, and we'll decide from there on out, what you'd like to use to solve the remaining exponential equations. But there is this overarching process that helps us solve the more advanced exponential equations. The first step is really key. You want to isolate the exponential expression. And the exponential expression is going to be the term that looks similar to this, where it's a number raised to some power involving the variable. And then the right-hand side will most likely just be a constant, so some number that doesn't involve x. And then what you could do is a couple of things. You can rewrite the equation in log format. That involves a log loop. Or what you can do is something called take the log or natural log of each side of the equation. Regardless of what you do, the equation is either going to be simplified, that's if you take the log or natural log, or based on a log loop, you might be just a few short steps away from solving for the variable. All right, but regardless, after this step happens, we should be in a position to isolate x using ordinary algebra. So that's step 3, is where you solve for the variable. And there's this little asterisk here because of how our final answers might need to be rewritten. If you use a log loop, then there's a good chance that you might need to use the change of base formula to get something that you can actually type into your calculator. In some cases, you might need to do the same thing when you take the log or natural log of each side. But I'll let you in on a secret. You're not really forced to use log base 10 or log base e, but the reason why it shows up in this technique is because there are buttons in the calculator. You can actually use any base that you want, and in some instances, when you choose the proper base, it leads to easier math. So we'll see an instance of that actually with problem 1. All right, but just know that if you're asked to approximate your final answer to like 2 or 3 decimal places, you might need to rewrite your answer using the change of base formula to get something that you can actually type into your calculator. So without further ado, let's look at some advanced exponential equations. In problem 1, we've got 3 times 5 to the power of x equaling 6. Before we consider step number 2, we have to make sure that the exponential expression is isolated. And our exponential expression in this case is 5 to the power of x. Is this isolated on the left-hand side? No, currently it's being multiplied by 3. So if I wanted to isolate this, what should I do to each side? Divide by 3. Okay, that's going to give us 5 to the power of x is equal to 2. So now that the exponential expression is isolated, we can move on to step 2, where we can decide to use a log loop or apply a log to each side. With this particular example, I'd like to show you a quick way of getting x isolated. pretty much right off the bat. I mentioned that you can use any log. You can use a log of any base. In this case, the log that we use should probably have a base 5, but it could have a base 10 or a base e, depending on what you're comfortable with. Let me show you what happens if we use a log base 5. So I'm going to introduce a log base 5 to each side of the equation. And on the left, inside this log, will be 5 to the x, and 2 will be in the second log. Now, why do you think I chose to use the log base 5? I'll give you a hint. Look at the left-hand side. The base of the log matches the base of the exponential. What did we just review about this kind of format? What happens with the log notation and the base of the exponential? They cancel, right? And then what's left over is the power. So by using a log base 5, we can actually cancel the base 5, and what's going to be left over on the left-hand side is that power of x. And on the right-hand side is log base 5 of 2. Now, I'm going to rewrite this using the change of base formula. And I believe my math lab likes to use the common log version. So you might see this not as log base 5 of 2, but rather log of 2 divided by log of 5. Okay, so this would be one of those what's so-called exact answers for x. You could punch this into the calculator to get an approximate value, and when you do so to 2 decimal places, you should get something to the tune of 0.43. And that would be an approximate answer. And I thought of a really clever name for this technique or this method. I'm going to call this the BS method. BS standing for both sides. Okay, so to each side of the equation, I applied a log base 5. So both sides get a log base 5, hence the BS method, both sides. For problem 2, I'm going to show you the log loop method. But if you look at how the equation is set up for us, the exponential expression is nowhere near being isolated. To start isolating it, let's subtract 8 from each side. That'll give us negative 2/9 to the negative x equals negative 5.5. Our exponential expression is not isolated just yet, but if we do something to each side, we'll get it isolated. What should we do to get 2/9 to the negative x isolated? Yeah, you can multiply or you could divide by -1. I would prefer division. And what that gives us on the left is 2/9 to the negative x, and on the right, positive 5.5. Now, I'm going to do a log loop. Once the exponential is isolated, you have the option to use the BS method, but in this case, I want to use the log loop method. And what that essentially means is we're just going to rewrite this in log format. Now, as a recap, when we write this in log format, We start at the base, which is 2/9, wrap around the right-hand side, and then finish off in the exponent. So it becomes log base 2/9. What number is going to go in the argument, folks? (5.5), and then this will equal -x. Now keep in mind, we want x by itself, and as soon as we do a log loop, it's actually back on the ground, as I like to say, but it has a -1 with it. So what I would do from here is maybe divide each side by -1. And what you're going to get for x is negative log base 2/9 of 5.5. Now again, this version of x usually can't be typed into the graphing calculator. So what you would want to do from here is maybe use the change of base formula. X equals negative log of 5.5 divided by log of what number? (2/9). All right, so that would be an exact version of x. An approximate answer for x would be 1.13. Yep, I used the change of base formula. No problem. All right, so we had the BS method for number 1. Number 2 would be the log loop method. Let's move on to problem 3. And once we wrap problem 3 up, we'll take a break. And we'll finish off problem 4, and then the rest of this afterwards. So with problem 3, I want to make a note that x plus 4 is the exponent of 2. Okay, so that's going to be helpful for our technique. And we have 2 to the power of x plus 4 equals 15. My question for you is this. Is the exponential expression isolated? In other words, is there anything in front of it, and is there anything behind it? So nothing's in front of it, and nothing's behind it. So this is isolated. Let me just jot it back down. My next question for you is this. Well, what method would you like to use for this one? The BS method or the log loop method? Yeah, okay, we can do the BS method. So the base of the exponential is a 2, and for this reason, you might want to use log base 2, BS wherever possible. So I'm going to introduce a log base 2 to each side. And going in the argument with the log on the left will be 2 to the power of x plus 4. And then with the log on the right would be 15. Now because the base of the log matches the base of the exponential, we get canceling. And what's going to be left over is x plus 4. And that's going to be back down on the ground. The log doesn't cancel on the right-hand side. In fact, it's going to kind of stick around for the entire rest of the problem. I'm not going to write the right-hand side and change the base format just yet, because what I want to do is subtract 4 from each side to get x by itself first. One thing to note is that 15 is the only number in the argument, so you don't want to mistakenly write this as log base 2 of 11, which would come from 15 minus 4. There's no log attached to this 4, so there would be no way of blending the insides together. But in order to get something that we can type in the calculator, you might want to rewrite this log expression using the change of base formula. So log of 15 divided by log of 2 minus 4. All right, and that would be our exact answer for x. Anybody want to punch this into the calculator and give us an approximate answer for x? Well, if you want, you can confirm this during the break. It's going to be negative 0.09. All right, any questions before we take our break? All right, I'll see you guys in about 5 minutes. All right, welcome back everybody. Let's go ahead and take care of the advanced exponential equations with problem 4. Our exponential expression in this case is e to the power of 2x. There is something in front of it, and that's the 5, which is being multiplied. So let's divide each side by 5. So on the left, we're going to have e to the power of 2x, and then on the right, let's leave that as 7/5. Now when it comes to an exponential equation where the base is e, I definitely prefer using the BS method because, we have a natural log, and the natural log key is actually in our calculator. So, it kind of lends itself to less steps. In other words, you wouldn't really have to use the change of base formula once we isolate x, and we'll see just that once we isolate it. So with e to the 2x equals 7/5, I recommend putting each side inside of a natural log. And on the left, the natural log will cancel out the e, and 2x is going to be left over. And that goes back down on the ground. And on the right, let's leave this as the natural log of 7/5. Next thing we'll do is divide each side by 2. And when you divide the right-hand side by 2, you want to put that 2 underneath the entire logarithm. It does not go inside of it. And that would be as far as we can go in terms of isolating the variable x. And there's no need to rewrite x using the change of base formula because we have a natural log key in our calculator. All right, and when you go to type this in, you should get something to the tune of 0.17. Does that make sense? Y'all still with me, right? Come on, guys, it's the final push. It's the final push. Just a little bit more to go. Let's move on to, did you work a lot of hours over this weekend, Kevin? Ouch. I'm so sorry. So I imagine after class you're gonna saw some logs. Just got off work at 7. Lord have mercy. That's cray. That's cray. All right, we'll make it though, folks. We'll make it either way. Okay, now we're gonna move on to solving advanced logarithmic equations. Yeah, overnighter life. There you go. I'm feeling a little tired this morning. I had a dream about mufflers. Woke up exhausted. All right, so we're gonna look at equations that involve 2 or more logs, and that's part of the reason why I wanted to go over those log properties at the start of class today. When we have equations that involve multiple logs, we want to do a little bit of rewriting. And this rewriting involves having all the logs on one side and everything else on the other side of the equal sign. Because once we have the multiple logs on one side of the equation, we can condense them into a single log. And what ends up happening is that it allows us to rewrite the equation in a simpler format. Let's say it's log base a of m equals n. And by simply doing a log loop, if the expression m has the variable x, what's going to happen after you do the log loop is that expression is going to go on the right-hand side and no longer be inside of a logarithm. And so by doing a log loop, you get to free up the expression that involves the variable x. And then we just solve from there. There's one little proviso though. With some log equations, you get multiple answers, and that's actually, or that should raise a red flag, because anytime we get multiple solutions to a log equation, there might be extraneous solutions, which, as a reminder, extraneous solutions are answers that we get just by pure algebra, but they don't solve the original version of the equation. If we get an extraneous solution, then we can either test it out by hand, or we can figure out that it's an extraneous solution using our graphing calculator. So I'll do the latter with you guys once we get some practice with solving these using the graphing calculator. But first, I want to show you how to solve a log equation algebraically. Here we have log base 5 of x plus 3, notice x is in the argument, equals 1 minus log base 5 of x minus 1. And there's a second log with x in the argument there. The first thing that we're going to want to do is move all of the logs to one side of the equation. And I think the easiest one to move is going to be the one on the right. We're going to add it over to the left. So this becomes log base 5 of x plus 3 plus log base 5 of x minus 1 equals 1. Notice that both logs have the same base 5. Moreover, they're being added together. That allows us to condense this into a single log base 5, provided we do what with the arguments? Multiply. Yep. So we're going to have to take x plus 3 and multiply it to x minus 1. Let's go ahead and FOIL that. This will be log base 5 of x squared plus 2x minus 3 equals 1. So notice that our equation is of that format, log base a of m equals n. In other words, once you have that side with the multiple logs condensed into one log, you're free to log loop. And let's see what happens when we log loop. Start at the base 5, wrap around the 1, and finish off in the argument. This will become 5 to the power of 1 equals x squared plus 2x minus 3. So if we kind of want to make reference to those exponential equations, this is akin to the log loop method. There is a BS method for log equations as well, provided that the equation is written in this format. So I'm going to say or, and what we could do alternatively is raise each side using a base 5. So check this out. The left-hand side, I'm going to write is 5 to the power of log base 5 of the quadratic expression. Now, if I do that to the left, I'm also going to have to do that to the right-hand side. What's going to happen on the left-hand side since we have 5 being raised to a log base 5? Well, the 5 and the log base 5 are going to cancel each other out. Yep. So x squared plus 2x minus 3 comes back down, and 5 to the first, the best we can do is just keep that as 5. So you're welcome to use whichever method you prefer most. Okay, you can use a log loop method like we have on the left, or you can use a BS method where we raise each side by the base 5. So either way, you should come up with the same quadratic equation. So I'm just going to solve one of them. Let's subtract 5 from each side with that first equation to get 0 equals x squared plus 2x minus 8. That's a quadratic expression that factors as x plus 4 times x minus 2. And we could set each factor equal to 0 to solve for x. And what we end up getting is 2 answers for x. And the fact that we get 2 answers for x means that we might want to consider there being extraneous solutions. But we'll revisit this in just a little while to see if there are extraneous solutions, and if so, which one is the extraneous solution. All right, so we're going to do that with our graphing calculator, but we'll do it a little bit later. So I'm not going to cloud anything just yet, but I will ask, do you guys have any questions about the process? Well, let's move on to problem 2. Another equation with multiple logs. We have a common log, so log base 10 of 7x plus 6 equaling 1 plus another log base 10, this time with the expression x minus 1. How do you think we should start this out? Yep. I recommend moving the log that's on the right over to the left. So the left becomes log of 7x plus 6 minus log of x minus 1 equaling 1. So we have multiple logs on the left-hand side. Notice the operation between them is subtraction. So if we do want to condense this into a single log, which we do want to do that, what should we do with the arguments? Should we multiply them together or divide them? Right. You got it. The numerator will be made up of the first argument, 7x plus 6. And the denominator will be made up of the second argument, which is x minus 1. It might be helpful to write the base 10 with this log, because when you do, it's a little easier to format the log loop, and it's a little easier to format the BS method. If we do the log loop, we'll have 10 to the power of 1 equaling that fraction. Alternatively, you could raise each side using a base 10. And on the left-hand side of the second equation, the base of the exponential matches the base of the log. So we get canceling, leaving behind the argument. And 10 to the first is 10. That makes sense? All right, so I'm going to go with the log loop method in terms of solving the rest of it. We do have to isolate x. And this is actually a rational equation. And like we've done in the past, what I would do is maybe multiply each side by the denominator. Okay, that'll cancel it out on the right-hand side, and on the left, you can distribute to clear parentheses. So 10x minus 10 equals 7x plus 6, and I'll have you folks drive it home. All right, go ahead and solve for x, and once you get it, report it in the chat. Yep, you got it. So I'm going to start by subtracting 7x from each side. That'll give us 3x minus 10 equals 6. Add the 10 over to get 3x equals 16. And you guys are definitely correct. X is equal to 16 over 3. All right, the approximate answer to that would be 5.33-ish. All right, well, I'm going to go a little bit out of order with our next page of notes. Let's save the graphing utility stuff for the very end. I do want to show you that this stuff does get used in the real world with this example, which has a function which gives the value of a car. It's the value as a function of x, where x represents the number of years old that it is. It says here the value v of a car that is x years old can be modeled by the following exponential function. We have v of x equals 19,705 times 0.848, and x is its power. Oops. Hang on, I gotta give my pen some juice. It just takes 15 seconds. All right, that should be good. And it says, based on the model, when will the car be worth $14,778? Keyword here is when. So we're actually looking for a value of x, which means that this figure right here would represent which variable from our function, x or v. Yep, this is a value of v. So what we're going to do is set up an equation using the exponential functions expression set equal to 14,778. So let's write 19,705 times 0.848 raised to the power of x equals 14,778. This is an example of one of those tougher or advanced exponential equations. And you may recall from earlier that our first step is to isolate the exponential expression. So what should we do to start things out? Should we subtract it, or should we do something else with it? Yeah, let's divide by that 19,000 number. Okay, so these will go away on the left-hand side. On the right-hand side, if you punch this in, you get something that's really, really close to 0.75. So let me show you that. 14,778 divided by 19,705. Personally, when I get these sort of values when solving exponential equations like we have, I tend to leave the fraction as is, but a more practical way of doing things is to perhaps round this decimal that we get once we crank it out in the calculator. And when doing so, the more decimal places you use, the more accurate your answer will be. And if it were me, I would maybe round to 4 decimal places. And even so, this would round to 0.75 regardless. So instead of using the fraction, let's maybe use 0.75 instead. That'll make the writing a little easier to handle. So let's write 0.75 for the right-hand side. And our mission now is to figure out a way of getting x back down on the ground. And you have 2 choices, right? You can use the BS method or you can use a log loop. But I want to show you something else that you could do. So let's say that we wanted to opt between using the BS method. Let's say that we wanted to use the BS method over the log loop method, but we didn't decide to use the base 0.848. Let's pretend that instead we applied the natural log to each side. We haven't seen that when the base is different than e. So I want to show you what happens. Let's put the left-hand side in the natural log, which means we'll have to put the right-hand side in it. Now, because the base of the natural log doesn't match 0.848, these will not cancel. Something else happens though, and that something else is the power rule. So even though the base of the log doesn't match the base of the exponential, meaning we can't cancel, we do get something that does happen still. And what happens is that the power will come down in front, and it becomes x times the natural log of 0.848. Nothing happens on the right-hand side either in regards to canceling. It'll still be natural log of 0.75. Now notice x is back down on the ground just by virtue of the power rule, and it's being multiplied to this natural log. Well, to get x by itself, we would divide by that natural log. Yep. And so these natural logs cancel each other out, and we get x is equal to the natural log of 0.75 divided by the natural log of 0.848. All right, so that would be as close to an exact answer as possible. And I say as close because we rounded 0.75. And I think we should probably do another round of rounding again, just to give a more practical answer to the context here. Remember, x represents the number of years. So whatever our approximate value of x is, that's how many years it's going to take in order for the value to depreciate to 14,778. All right, so we can go ahead and type this in. Natural log of 0.75 divided by the natural log of 0.848. All right, so I'm going to round this to 2 decimal places. 1.74 years. Okay, how do you like it? Is that what you guys are coming up with in your calculators? Okay. Well, let's keep those calculators warmed up because we're going to use them to solve some equations for which algebra cannot be used. And then we'll also use them to verify some of our equations where algebra was able to be used. So I'm going to scooch back up to the top of this page and begin the discussion on how we use calculators to solve. Specifically, like why we would use them versus algebra. The funny thing about exponential and log equations is that it's very easy to get used to solving them algebraically, but there are some curveballs that can be thrown into the equation for which you end up going in circles. Like you apply a log and then you're like, okay, now I'm going to rewrite an exponential. Okay, now I'm going to rewrite in log. It's very easy to get caught in a cycle with some of these equations. And if you've done everything, 100% correct, and you're not able to really isolate x regardless of what you do, then that's probably a sign that you need to solve it using the graphing calculator. And the methods for solving don't change on the graphing calculator. We can use either the zero feature or the intersect feature. Now, in a lot of cases, just based on how the equations are written, they're typically not written with zero on one side of it. So what you'll find is that if you're asked to solve an equation using a graphing calculator, it's most likely going to require the intersect feature. Case in point, with example 1, we have e to the 3x on the left and negative x plus 5 on the right. So this is definitely a situation where we'd probably want to consider using the intersect feature. And what that means is we'll have to define the left-hand side as our y1 and the right-hand side as our y2. So let's go to our graphing calculators. And y equals, to enter e to the 3x and y1, we'll press second natural log. And your calculator might have a set of parentheses already open. Mine puts me in the exponent, but because the exponent is 3x, I prefer using the parentheses. So although it might not be necessary with my version of the calculator, I'll still use parentheses around 3x. And then for those of you that had like e caret half open parentheses, type in 3x and then close them off. Then we'll go to y2, small minus sign, x plus 5. And then we'll do a zoom 6. All right, how do those two graphs look on your end? Okay, let's go ahead and use the intersect feature. It looks like they're intersecting somewhere in quadrant 1, a little bit close to the y-axis. Let's press second, trace, and we'll use option 5. And we're going to scooch that blinking cursor as close to this point of intersection as possible. I think right here, above it or underneath it will be good enough. As long as you're in the general vicinity, go ahead and press enter 3 times. And to 2 decimal places, x is approximately 0.50. Is that what you guys are coming up with? Okay. Let me go back here. So e to the 3x did something like this. And then negative x plus 5 did a little something like that. And this is roughly 0.50. I'm not sure what the y coordinate was, or I don't remember it, 4.50. We are solving for x, so the x coordinate of 0.50 will be our official answer. And that's how we do it on the graphing calculator. If you look at problem 2, it's another example where we might want to use the intersect feature. And this is one that I'm going to give you a shot with. Okay, we do have the common log button in our calculator. So this is typable, if that's a word. So the left-hand side will be our y1, and the right-hand side will be our y2. All right, so I'm going to give you a couple minutes to punch that in, and then use the intersect feature if there are any points of intersection. Kevin, you using the small minus sign for that log? All right, let's go over the answer. So small minus sign. Whoa, 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 whoa. What's going on here? Hey. Here we go. Okay. All right, let's try this again. Minus log x plus 5. Jump down to x plus 1. Do a zoom 6-aroo. There's y1. There's y2. All right, so second trace, option 5. Scooch to the point of intersection as close as you can. 1, 2, 3 on the enter key. And we're looking at roughly negative 0.81, comma negative 0.62. All right, so our approximate answer would be negative 0.81. So very good. Everybody else getting negative 0.81 as well? So I just want to talk about why we might want to use a calculator for an equation like this. Notice that we have x inside a log, and we also have it over here on the right, but it's not inside the log on the right-hand side. We would be forced to do a log loop in order to get x plus 5 out of the argument. And what ends up happening is that, in the power of 10, we're going to have the variable x. So in one instance, we get x out of the argument of the log, but at the same time, we put x as the exponent. So we end up going back and forth between x in the log and x in the exponent, and you wind up going in like a circle, in which case our algebra breaks down and we wouldn't be able to get x by itself. So thank goodness for the graphing calculator. At least we can get an approximate answer to something like this. Now that's all fine and dandy when you're using either the log or natural log, because those are buttons in our calculator. But what if we wanted to solve something like problem 1 from our advanced logarithm equations part? All right, how would we type something like this into our graphing calculator? Well, let's go over that. Break this problem off. So let me write down the original version of the equation. And you might recall this is an equation we got two answers to, x equals -4 and x equals 2. Let's see if any of those are extraneous. So the original equation was log base 5 of x plus 3 equaling 1 minus log base 5 of x minus 1. So no side is 0, meaning that we'll want to opt for the intersect feature. And that means the left-hand side will be our y1, and the right-hand side will be our y2. Now, in the graphing calculator, most of us don't have the capability of typing in log base 5 of x plus 3 as is. So instead, I'm going to give you a way that works for everybody. And that way is using the change of base formula. So instead of log base 5 of x plus 3 for y1, let's type in log of x plus 3 divided by log of 5. Oops, not log base 5. I meant log of 5. There we go. And then in y2, we'll type in 1 minus log of x minus 1 divided by log of 5. Okay, so these two versions of the log come from the change of base. All right, you ready? Here we go. So in y1, let's press the common log key, log, and x plus 3. Be sure to close off the argument because that second log goes underneath the first log, log of 5. And then in y2, 1 minus log x minus 1 divided by log of 5. Let's do zoom 6. Here comes y1, and there's y2. All right, I'm going to give you a moment to use the intersect feature to find this point of intersection that's in quadrant 1. But before that, according to our graphs, how many answers does our equation have? Yeah, according to our graph, there's just one point of intersection. So one of those answers that we got from algebra is extraneous. Now, if you use the intersect feature, you're going to find that the point of intersection is at 2, 1. So let me sketch this all out. Here's what y1 did. And then here's what y2 did. Something like this. So it would appear as though our graphing calculator indicates that there's just one answer for x, and that would be x equals 2. So going back to our algebra solution, we had two answers for x equals 2, but also x equals -4. So because of what our graphing calculator is providing us, x equals -4 would be one of those extraneous solutions, meaning x equals 2 is the true solution to our equation. All right, do you guys have any questions about what we went over today? Would you like to do a practice problem? Let me just conjure one up for you. Okay, hang tight. All right. Here's a you try. Log base 8 of x plus 6 equals 1 minus log base 8 of x plus 4. All right, go ahead and solve this algebraically. We'll go over the answer, and if we have time, we can look at the graphical solution. All right, so go ahead and solve for x. Check in with you in just a little bit. All right, I'm going to start writing out my solution. Let me know if you have any questions along the way. I first started out by adding the log base 8 on the right over to the left. So it becomes plus log base 8 of x plus 4 when it goes on the left, and then 1 on the right. These are two log base 8s now being added together, so we can condense that into a single log. Make sure that you keep the base 8, by the way. And then inside the argument, we should have multiplication between x plus 6 and x plus 4. All right, foiling that out, we're going to get x squared plus 10x plus 24 in the argument equaling 1. Now, let's release x squared plus 10x plus 24 out from the argument. What number goes on the right-hand side? This is one of the most common errors I see. So if we log loop, which is one method from the log to the quadratic equation, we should have 8 to the power of 1. Yep. So you could do log loop, or you can raise each side by a base 8. And if you raise each side by a base 8, those cancel, and then whatever's left inside the argument is set equal to 8. So let's now subtract 8 from each side to get x squared plus 10x plus 16 equals 0. And it looks like that factors x plus 8 times x plus 2. So again, we get two answers for x. X equals negative 8 and x equals negative 2. Did anybody, was anybody able to view this problem on the graphing calculator and determine whether or not one of these is extraneous? Okay, well, in the interest of time, in y1, you would want to type out log of x plus 6 divided by log of 8. Okay, that's by virtue of the change of base formula. For y2, you'd have 1 minus log of x plus 4 divided by log of 8, again by the change of base formula. And what I found is that y1 did a little doohickey like that, and then y2 was oriented this way. And there's just one point of intersection, and that point of intersection would yield the answer of x equals negative 2. So of these two values of x, our graphing calculator tells us that negative 2 is the real answer, whereas x equals negative 8 is extraneous, which I'm going to write as EXTR. Alrighty, folks, that wraps up class for today. Any final questions before I dismiss you?